Hi everyone, today we're going to be starting section 5.3, which is solving trig equations. Um, we're going to spend 3 days in this section. There's a bunch to learn. And I want to start off by thinking about this visually, though most of the time we won't be, but I think the visual element will really help you think about this if you get stuck. So let's start with sine x equals root 3 over 2. Well, we know from the unit circle, sine, the upness, the y value, is root 3 over 2 at x equals pi over 3 and 2 pi over 3. But let's think about this graphically for a moment. Our sine graph goes up and comes down, and back up and back down, and it even goes backwards forever. Unlike inverse sine, which has that restriction, sine goes on forever. So there's our graph of sine x, but we're wondering when sine x is equal to root 3 over 2. Well, I see lots of solutions. Here's the ones that we found originally. Between 0 and pi over 2, also known as quadrant 1, there's a solution, and that solution is pi over 3. And then over here, between pi over 2 and pi, that's quadrant 2, there's another solution, and that's the one 2 pi over 3. So if the directions say, as they often do, find the solutions on 0 to 2 pi, we've done that. We found all those solutions. And sometimes the directions say find all solutions, or solve, period, not solve on 0 to 2 pi. So if the directions say solve or find all solutions, then we need to be able to find this one and 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 all the other ones. Well, let's think about these solutions for a second and use the periodic nature of sine to help us out. How far is it from this point on this downslope to one that looks just like it, the next solution, also on that downslope? Well, that would be 1 period. And since the period of this sine graph, there's no b value here, is 2 pi, I know the distance from this point to this point is 2 pi. So I could say 2 pi over 3 plus 2 pi will get me another solution. I could also go 2 pi in the other direction. And I could keep adding or subtracting increments of 2 pi to find more and more solutions. And I could do this an infinite number of times. And so the way I'm going to represent this is by saying, taking my first solution, 2 pi over 3, and then adding 2 pi n, where n is an integer. So maybe n is 0, in which case that's my answer. Or if n is 1, 1 times 2 pi is 2 pi added to 2 pi over 3, so that would find this solution. Or if n were negative 1, we'd be finding this solution. So this is our little machine for generating the infinite solutions. Just like last semester when we had our parametric solution, here we're not going to have any z equals a thing going on, but we are going to have an infinite number of solutions defined in this way. So what about this other point, the point on the upslope, the one at pi over 3? How far is it from the next point on the upslope? Well, that's still 1 period, that's still 2 pi, and so I'm going to say that second solution will be pi over 3 plus 2 pi n. Now, if I ask for all solutions and you only give me 0 to 2 pi solutions, the problem is wrong. If I ask for 0 to 2 pi solutions, but you give me all solutions, the answer is wrong. So you really, 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 really have to pay attention to what the question is asking in order to figure out which of these solution types you're doing. Are you doing the specific solutions on 0 to 2 pi, or are you doing all solutions? These both are the all solutions answers. Okay, so let's go through some problems now, and let's see about doing them both as 0 to 2 pi and as all solutions. Okay, here's our first one. I want to look at square root of 3 plus 2 sine theta equals 0. Well, if I subtract root 3, I'm going to see 2 sine theta equals negative root 3. And if I divide by 2, I'm going to see that sine of theta equals negative root 3 over 2. Well, let's start with the 0 to 2 pi solution. We know that sine is negative root 3 over 2 twice on the unit circle. We see that on the graph of sine. There's this solution here between pi and 3 pi over 2. That's in quadrant 3. And we see this other solution here between 3 pi over 2 and 2 pi. That's in quadrant 4. So when in quadrant 3 or quadrant 4 is the y value or the upness negative root 3 over 2? Theta equals 4 pi over 3 and 5 pi over 3. But if I were asking for all solutions, we would come up with theta equals 4 pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. And before you say, Mr. Kukla, do I always just slap on the plus 2 pi n to my solutions in order to get the all solutions answer? Well, the answer to your question is almost always. And we will be looking at some of those examples later. I don't think we get to any of them today, but I think we do have one of them today. But on Monday, we'll see more. I'm sorry, on Tuesday, we'll see more. Okay, so there's the first one. And how about this one? We've got something in factored form, 2 sine t plus 1 to cosine t minus 3 equals 0. Okay, so I want to set each factor equal to 0, and that's going to be 2 sine t plus 1 equals 0, or sine t equals negative 1/2. And here, I'm going to get cosine t, 2 cosine t equals 3, or cosine t equals 3/2. Now, please note, 3/2 is greater than 1. And the biggest x value on the unit circle is 1. So can cosine ever be equal to a number bigger than 1? No. This doesn't produce any solutions for us. Over here, however, I know when sine is equal to negative 1/2. That happens at 7 pi over 6 and at 11 pi over 6. So those are my 0 to 2 pi solutions. And my all solutions answer? That would be 7 pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n. I want to take a moment to look at this original graph on the calculator screen because I think a lot of times students don't use their calculator effectively. Let me get this light on. Does that help? Gosh, you can't get any light on this screen. There we go. I'll just hold it awkwardly for a few minutes. Okay, so I'm going to type this in and then I'll tilt it appropriately. I'm typing in y1, 2 sine t plus 1, close parentheses, open parentheses, 2 cosine x minus 3, close parentheses. So there we go. Notice here that you have to close the parentheses on the sine and cosine before you add the 1 and subtract the 3. Next, I'm going to go over to my window, and I want to go from 0 to 2 pi. And I think my answers are pi over 6 things, so I'm going to set my scale at pi divided by 6. Okay? My y values. Well, this is a sine graph. Sine graph goes from -1 to 1. So, or a cosine graph, that goes from -1 to 1. So I'm going to change my y min to be -1, my y max to be 1, and I'm going to hit graph. Oops, I still have a problem from calculus here. Let me turn that off. Okay, so we're looking for x-intercepts. How many x-intercepts do we see? 1, 2. And we can count, because we set our scale on pi over 6's. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6 is one solution. 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6 is the second solution. So I strongly encourage you, especially on a test, to check your answers. I can confirm these answers by looking at that graph. I have to have a decent viewing window with a proper scale to make it easy, but the effort involved in that is not very great, and it will certainly keep you from thinking that there are any solutions being created over here. Okay, next. Secant squared x equals 4. Or we might see secant squared x minus 4 equals 0. So here I would simply add 4 to both sides, and then that would bring me over here. Now, I don't know anything about secant. I mean, I guess I could take the square root of both sides. So I get secant x equals, when I take the square root of both sides, what is it that I'm supposed to remember? Please remember plus and minus. If I don't have that plus and minus, this answer will not be, I'll only have half the answers. So secant equals plus or minus 2. Well, I don't know from secant, but I know cosine is the reciprocal of this. So what's the reciprocal of 2 over 1? Plus and minus 1/2. When is cosine equal to plus and minus 1/2? Well, that happens when our angle is pi over 3 and 5 pi over 3 for positive 1/2, and 2 pi over 3 and 4 pi over 3 for negative 1/2. I get 4 solutions here. And again, if I want, I can always graph the original secant squared in y1, 4 in y2, and then set my scale, my x scale, on pi over 3's, and do second calculate intersect to see these 4 solutions. Now, this would be the 0 to 2 pi solution, but what if we were asked for all solution? Well, you could, as many of you will want, simply write 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. And that's a lot of writing, and I'm lazier than that. And we're humans, so let's use our brains and think about how we could do less work here. Let's look at our answers. We have this answer here at pi over 3. We have this answer over here at 2 pi over 3. We have this answer down here at 4 pi over 3. We have this answer over here at 5 pi over 3. Well, how far is it from this answer to this one? It's half a circle, or pi. And how far is it from here back to there? That's another pi. And since the distance is the same both ways, instead of writing this one plus 2 pi n and this one plus 2 pi n, I could just write pi over 3 plus pi n. And I notice the same sort of thing happens with the 2 pi over 3 and the 5 pi over 3. This is a distance of pi. This is a distance of pi. And because those distances are the same, I can just list one of them and say, well, they're all going to be pi apart from each other. So this is what you can write. I won't mark it wrong, but this is what I prefer because it's tidier. Better to be correct than not sure how to do this, but this is a lot less time and writing to write this solution. Okay? All right, next, let's do a tangent problem. 3 minus tangent squared theta equals 0. Well, if we add tangent squared to both sides, we'll get 3 equals tangent squared beta. And we don't want to know what tangent squared is. We want to know what tangent of beta is, or even better, beta is. So we'll take the square root of both sides. What is it that happens over here? We get tangent beta. And what happens on the other side? Well, we know there's square root, but don't forget the plus and minus. If you forget the plus and minus, you're going to be throwing away half the solutions. And we get 3 over 1. Okay, so when is tangent 3 over 1, or root 3 over 1? And the answer is, I don't know. But if I divide each of these by 2 and think about tangent as sine over cosine, then I think, well, I know when sine is root 3 over 2. That's when cosine is equal to 1/2. And I want all of them because I want the plus and minus versions. So beta is pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. We get 4 solutions on 0 to 2 pi. And I believe these were the solutions we just saw before for secant squared minus 4. So we could say beta, if we were doing all solutions, beta equals pi over 3 plus pi n and 2 pi over 3 plus pi n. Yes, you're welcome to write pi over 3 plus 2 pi n, 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. Oh, but goodness, that takes a long time. Okay, so we've got our all solutions case, and we have our 0 to 2 pi. Next, how about this one? 4 sine squared theta minus 3 equals 0. Well, that's going to be 4 sine squared theta equals 3. That's going to be sine squared theta equals 3/4. And when we take the square root of both sides, that's going to be square root of 3 over square root of 4. Don't forget that plus and minus. So we'll know that sine theta equals plus and minus root 3 over square root of 4 is 2. We've just seen that twice before. On 0 to 2 pi, our solutions were theta equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay. Really, I'm just trying to tell you, don't forget the plus and minus when you take the square root of both sides. Okay, how about something a little more interesting and a little different? Tangent squared x sine x equals sine x. Now, you might be tempted to do this. Don't. Bad things often happen when we divide by a trig function. Let's follow this through and see what occurs when we both divide by sign and don't divide by sign. Okay, so sine divided by sine would be 1, and these would cancel, and so I'd have tangent squared x equals 1. I take the square root of both sides, I get tan x equals plus or minus 1. Tangent x equals 1 when sine over cosine equals 1. Well, what has to be true about these two values if when I divide them, the result is 1? They have to be the same number. And that happens when I have root 2 over 2 over root 2 over 2. But remember, we're looking for plus and minus 1. So that's going to occur when x equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And so we feel like there are going to be 4 solutions here. And they're all going to be at pi over 4s. Well, let's take a look at this graphically for a moment. I'm going to type this into the calculator. In y1, I'm going to type in parentheses tan x close 2 parentheses squared times sine x. Oops, I'm not typing that in y1. Let's try again. Okay. Parentheses tan x close 2 parentheses squared sine x close parentheses in y1. In y2, I'm typing in sine x. And I still want the 0 to 2 pi graphing window, because that's where I want to check my solutions. These solutions were all 0 to 2 pi. Going from -1 to 1 is fine. I'm going to set my x scale this time on pi divided by 4, because all of our solutions are pi over 4 based. And then I'm going to hit graph. There we go. And how many points of intersection do we see? 1, 2, 3, 4. Mr. Google, what's the big deal? Well, do we really see 4? Let's think about that again. Here's the pi over 4, here's the 3 pi over 4, here's the 5 pi over 4, here's the 7 pi over 4. But they're also intersecting over here, and they're intersecting here. And if we included 2 pi, they'd be intersecting at 2 pi as well. That means when we divided by this sign, we threw solutions away. Don't throw solutions away. And the way to avoid throwing solutions away is don't divide both sides by a function. Well, a trig function in this case. That's problematic. It can be done. We'll probably do it in the next couple of days. Yeah, don't do that. So don't do this problem by dividing both sides by sine. So how should you do this problem? Well, let's go back to the beginning. We had tangent squared x sine x equals sine x. Subtract sine x from both sides. Sine x minus sine x is 0. Now, you can't subtract these. It's like subtracting 5x minus 5. Just because they both have a 5 doesn't mean I can subtract them. So I can, though, write tangent squared x sine x minus sine x. And you might be saying, well, Mr. Kupla, what good is that? Well, I noticed that both of these terms have a sine x. And so I can factor out the sine x. Tangent squared x minus 1 is left over. This we already solved, gave us solutions of pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But look, now we've got sine equal to 0. And when is sine, the y value, equal to 0? Well, that happens when the angle is 0, pi, or 2 pi, 3 pi, 4 pi, and so on. So I've actually got 6 solutions. All right, so this is my 0 to 2 pi solution. 0 to 2 pi solution would be 0, pi over 4, 3 pi over 4, pi, 5 pi over 4, 7 pi over 4. Please note, 2 pi is not included. Many people lose points on the next test because with this list, they also write down 2 pi. No, this does not include 2 pi. Do not write down 2 pi as one of the answers. Okay, now let's talk about the all solutions case. The all solutions case here could certainly be written in this really tiresome, cumbersome way, and only because I love you so much will I write this one time only. 2 pi n pi plus 2 pi n, pi over 4 plus 2 pi n, 3 pi over 4 plus 2 pi n, 5 pi over 4 plus 2 pi n, and 7 pi over 4 plus 2 pi n. That's a lot. That's crazy. Let's take a look. How far is it from my solution at 0 to my solution at pi? Well, it's pi. And how far is it from that solution back to one that looks like this? It's pi. So I could just do 0 plus pi n. In fact, 0 plus pi n is just pi n. So instead of writing all this, I'm just going to write pi n, comma. Now what about all these pi over 4 solutions? Let's take a look at them. So here's pi over 4, here's 3 pi over 4, here's 5 pi over 4, here's 7 pi over 4. Now you might be saying, well, Mr. Kukla, those are pi apart, and so you could write pi over 4 plus pi n. And you sure could. And you could also do 3 pi over 4 plus pi n. And that's pretty good, but we can do better. No, really, look. How far is it from pi over 4 to 3 pi over 4? It's pi over 2. And how far is it from 3 pi over 4 to 5 pi over 4? Another pi over 2. And from 5 pi over 4 to 7 pi over 4, another pi over 2. And then from 7 pi over 4 back to one that looks like pi over 4 would be another pi over 2. I could add pi over 2 each time. And just write one of them. So my all solutions answer would be pi n and pi over 4 plus pi over 2 n. That's a lot less writing than all this writing. Okay? Okay. Next, factoring. It's going to be something we need to do. 2 cosine squared y plus cosine y equals 0. All right. Don't subtract this from both sides, because if you do, you'll probably want to divide both sides by cosine. Don't do that. Instead, factor. Factor a cosine y out. So cosine y, 2 cosine y plus cosine y divided by cosine y is not 0, it's 1. Don't forget that 1. Cosine y over cosine y does not equal 0. Cosine divided by cosine is 1 over 1, or 1. Okay, don't lose that 1. So now we have factored form. We can set each factor equal to 0. We get cosine y equals negative 1/2, and cosine y equals 0. Well, cosine y is negative 1/2 when y equals 2 pi over 3 and 4 pi over 3. And cosine y equals 0 when y equals pi over 2 and 3 pi over 2. And so I'm going to get 4 solutions on 0 to 2 pi. Again, I can always graph this on my graphing calculator to check. We can also think about the all solutions case. And the all solutions case, here I can see that these are pi apart from each other. So I can write pi over 2 plus pi n. But what about these? We've got 2 pi over 3. We've got 4 pi over 3. This distance is 2 pi over 3. This distance is 4 pi over 3. Since these distances aren't the same, I can't write a shortcut here. I have to write 2 pi over 3 plus 2 pi n and 4 pi over 3 plus 2 pi n. Okay? All right. Next, I think I only have 2 more that I want to look at with you. This one, sine squared x plus sine x minus 6 equals 0. Well, that's a trinomial. That's like x squared plus x minus 6. And just as you would factor this as x plus 3 and x minus 2, and then set each factor equal to 0, to get x equals negative 3 and x equals positive 2, here you're going to factor this as sine x plus 3 and sine x minus 2. And then we'll set each factor equal to 0. Sine x plus 3 equals 0. Sine x minus 2 equals 0. So we know that sine x equals negative 3, or sine x equals 2. And when is the y value 2 on the unit circle? Never. We know from graphing sine that the highest sine goes up to is 1. Sine can never get to 2. Furthermore, the lowest sine goes is negative 1. Will sine ever get to negative 3? No. So this has no solution. No solution is definitely possible in these problems. Okay, last one I want to look at with you is this one. Sine x equals 0.6. Well, I don't know 0.6 from my unit circle, but I do know, because we've done section 4.7, that I could solve for x by doing the inverse sine of both sides. And I would get that x, because sine inverse and sine cancel each other out, equals sine inverse of 0.6. My calculator, remember, is set in radians. My calculator says the inverse sine of 0.6 is, the inverse sine of 0.6 is 0.6435. Okay, and that seems like a decent answer. Why not? Well, let's think about this graphically again. On 0 to 2 pi, how many times will sine be positive 6? Or positive 0.6, I should say. Here's pi over 2, 1. Here's 3 pi over 2, negative 1. The line y equals 0.6 is about here. So I see 2 solutions. Now, this one is between 0 and pi over 2. So, since negative pi over 2 to pi over 2 is our restriction for inverse sine, lo and behold, this is the only solution our calculator comes up with. But we know there's a second one. Now, old school, we would use freaky reference angle formulas to figure this out. New school, what I want you to do is pick up your damn calculator, graph this in y1, graph this in y2, and do second, calculate, intersect. So let me type those in. I've already got sine x typed in y2, so I'll just type 0.6 in here. And then 0 to 2 pi is great for ours. And the y value should be fine, so I'm just going to graph. There's y equals 0.6. And there's our sine graph, and we see the 2 points of intersection. Do we? That's better. And we'll do second, calculate, intersect, and I'll bring my cursor close to a point of intersection. Let's do that first point of intersection. Enter, enter, enter. And down here, note the answer was 0.6435. Good. But now we need to find this second solution. So second, calculate, intersect, and bring your cursor over to that, close to that second point of intersection, and hit enter once, twice, thrice. And the answer I get there for that second solution is 2.498. So 2 solutions. And if I had to write the all solution case here, I'd write 0.6435 plus 2 pi n at 2.498 plus 2 pi n. Okay? So there's the all solution, and our 0 to 2 pi solution is just those two. Well, that's our introduction to solving trig equations. We'll be doing more when I see you next, but we'll be assuming that you know how to do this. So please make sure you do this homework tonight, because we're moving on with more solving techniques next time. All right, take care. See you soon.